Okay, relative strengths of acids and bases. I've just written out part of the table from your book to show that we have a list of acids in decreasing acid strength going down the column here. On the other side we have the bases, which are the conjugate bases of each of these species. You can see for each, as we move from left to right, we're removing an H plus to create the bases. Now, the couple of things you should see in this table is that first we have the strongest acids at the top, weakest acids at the bottom, and then the conjugate, since these are not just thrown in here, they're the conjugate bases of each of these, that the strength of the bases works in the opposite direction. So the weakest acids have the strongest conjugate bases on up. So the strongest acid that we have is HClO4. The weakest base is then ClO4 minus. So you should be aware of that and be able to work with this table. On my exams I'd give you this table, the one from your book or something similar, which will have a lot more of the acids and bases in it. But I'll come back to this table. So consulting that table, name an acid that is stronger than HBr. So give you some flexibility. Here's HBr. So any acid above it we can use. So just write in HI. Or H2SO4 or HClO4. Name an acid that is weaker than HNO2. So again, we go back to the table, HNO2, so I just picked the one below it, but anything below it can be used. Name a base that is stronger than I minus. So just remember how it goes. I minus, I want a stronger base, so I have to go down. To get, so we'll go to Br minus, but it can use anything that I wanted to. So it's stronger, weaker, yeah. Okay, determine the conjugate base of HCl and then determine a base that is weaker than this base. Well, the conjugate base is Cl minus. You should know that offhand. And then look at Cl minus. Oh, I don't have it in here. Oh, good job, Mark. So HCl would go here, Cl minus would be here. And then what I want, so we have our base. Determine one that's weaker. So we just have to take anything above Cl minus. So I'll take HSO4 minus. Okay, so just be able to work with that table, and you'll have the complete table, so it won't have anything missing like that one did. Put the members of each set in order of increasing acid strength. So big thing here is increasing. Make sure you get that right. On my exam, a lot of times people put them in the correct order. Well, they put them in the reverse order, I should say. Everything's right except they put them backwards, and we don't have to take away points, even though students says, well, you know, I set them up that way. So I'll show you how to avoid any problems along that line. Now, when you see a set of acids, you know they're acids because you have the hydrogens here. So those are definitely acids. Now, how do they differ? You have oxygen, sulfur, tellurium, and selenium. Those are all in group 6A. And you'll have your periodic table. So we have oxygen, then sulfur, then selenium, then tellurium. I'm just going to double check on tellurium to make sure. You can see that as we move down, that's how they are set up on the periodic table. So as we move down a column, our first rule here says, where is it? In going down a column of elements to the periodic table, the size of atom X increases, and so the HX bond strength decreases, and the strength of the binary acid increases. So what they're saying is that the oxygen is bonded to two hydrogens here, and then the sulfur, so it has a certain size. The sulfur is larger, so we can just make them all circular. And then selenium is larger still. And then the tellurium is monstrous. I might have to get another piece of paper for the other ones here. So, well, the bond is so long for tellurium that these hydrogens barely know that they're attached to it. Since they barely know that they're attached, so their bond strength is going to be, bond length is very long, their bond strength is going to be very weak there. They more easily jump into solution, which makes it a stronger acid. So increasing acid strength, we'd put H2O, H2S, H2SE, H2TE. Now what I did here was I went from left to right like you'd expect if you're going to put them in order, but then I also put the inequalities in between, so there is no problem there. So if a student were to write this backwards, but use the correct equalities, inequality signs, that'd be fine by me. But if you just put them in order, let's say you put this one first, and then this second, third, and fourth, and you don't put anything in between, it will look to me like you've set them up backwards. So just be careful. Okay, I'll find my way back to the chapter here. Okay, now look at the next set here. We have hydrogens again in each of these. So these are all, well, they're not all acids, but we're going to treat them as if they are. Now look at, they're all from the same row. They're all from the second row of the periodic table. And we have carbon, nitrogen, oxygen, and fluorine. Now, the rule then, going across a row, the electronegativity increases, so the HX bond polarity increases and the acid strength increases. So as we go from left to right, we should expect the acid strength to increase. Now it's pretty obvious if we do that, if we put the carbon and then nitrogen, water, and fluorine, or oxygen then fluorine. Well, first, this is the only one that's called an acid. This is hydrofluoric acid, so that should be the strongest one. Then water we know is amphoteric or amphoprotic. It can be an acid or a base. Ammonia is just a base. So we know that it has to be down here. And then methane is neither. It's so inert that it doesn't do anything. So that would appear to be the best way of sequencing them. Also, when you have something that's an acid and none of the rest of them are, then this one must be the strongest, and then the rest have to fall into place. The nitrogen can't flip with the oxygen. You can't have the carbon over here. If you're just looking at the central atom and you see they're all in the same row, the fluorine is going to be the highest, or have the highest strength, and then the rest have to follow. So it always goes, once you've pick the strongest one, the rest should fall into place, even if you're not quite, you can't quite pick it out at first. So here we have the next rule. We have hydrogens, so these are definitely all acids. So unlike the ammonia there in the last one, but these are all acids. They all have bromine as the central atom. The only difference is the number of oxygens. Well, the more oxygens you have, the more polar that bond is going to be to the hydrogen, and so the weaker the acid is going to be. So HBrO4 will come first, will be the highest, and then it has to go in this order. That's the thing. Once you've picked that top one, then it's got to be 1 oxygen, 2, 3, 4. If I don't put all of them in here, let's say I just have 4, 3, and 1 oxygen, well, then that one gets left out, but it's still in the sequence. So know these rules. Now, it doesn't have to be bromine. It can be chlorine in here. It could be iodine, any central atom. And just as the oxygens go up, the acidity of the species goes up, or the acid strength goes up. Then we have hydrogens, so all acids. All three have 2 oxygens, but the thing that's changed is the central atom. When we get to this one, then for a series of oxoacids, so they're acids that contain oxygen, of the same structure, differing only in the atom Y, the acid strength increases with electronegativity. So the most electronegative, as we move, the electronegativity increases as we go from left to right, and then goes from bottom to top. So the highest, they're all in the same group, so the chlorine is the highest up there. This is going to have the highest electronegativity, and so it's going to be the strongest. So that's how we set them up. So those are the 4 rules. And really, with the stuff in the book and the ones that I do in the lecture, plus these, I've covered most of the sequences that you had. There's only so many. This one is kind of a weird one because I had to use something, I wanted to use something different. So this could be chlorine, and iodine, but that's it. These bromine, chlorine, and iodine, these are the only ones that really form oxoacids very much. We have sulfur can too, but so I might be able to put those in there, but we really don't have that many possibilities. So on top of knowing the rules, if you do the ones in the book, the ones here, and the ones from the lecture, you probably covered them all.